Hello everybody, I'm Franco Angelini from University of Pisa, and the title of this talk is Optimal Control of Articulated Soft Robots. Let's start from the motivation behind this work. If you apply to soft robots optimal control techniques which were designed for rigid systems, you end up having a degradation of the performance which is somehow proportional to the compliance of your system. For this reason, in this work we aim to design an optimal control framework based on differential dynamic programming to exploit the intrinsic compliance of articulated soft robots. The proposed method plans the state trajectory and the input torque, and in case of robots actuated by variable stiffness actuators, it plans also the stiffness profile. The method efficiently computes the forward dynamics and also uses the analytical derivatives of your system. Additionally, a locally optimal feedback policy is also derived thanks to the DDP algorithm. All these points are finally validated through simulation and experiments. The model we consider is the classic one of articulated soft robots, with the difference that some of the joints can be unactuated. This lack of actuation is modeled via the selection matrix S. We formulate the discrete time optimal control problem for soft robots as shown here. The first line is the objective function, then we have the numerical integrator, the forward dynamics, and eventually a set of constraints. Before moving on, let me recall a few preliminaries on DDP. This algorithm iteratively performs a backward pass on the nominal trajectory to compute a new control input. Then, the forward pass is executed to compute and evaluate a new nominal trajectory. It is important to mention here that during the backward pass, locally optimal feedback gains are also computed. The forward dynamics can be written in a compact form. The link side dynamics can be efficiently computed via the articulated body algorithm. Then, the motor side dynamics can be computed relying on the analytical inversion of the matrix B, which in our case is a diagonal matrix. Thanks to the block diagonal form of the effective matter inertia, we can independently compute the partial derivatives on the link side and on the motor side. However, instead of numerically computing the derivatives, we rely on the more efficient analytical differentiation. Clearly, depending on the system under consideration, we will have different derivatives. As we mentioned before, the backward pass outputs also locally optimal feedback gains. So, to increase the performance of the task, we can rely on these feedback terms instead of relying only on the purely feed-forward control. We validated the framework via simulation and experiments. For the simulations, we executed tests with different types of tasks, different types of actuations, and with a different number of active and passive joints. For instance, we also simulated an underactuated compliant arm with only one actuated joint and 20 passive ones. With all the mentioned systems, we executed 20 different simulations to compare the efficiency of numerical and analytical differentiation. The results in this table show that the number of iterations for convergence are lower in the case of analytical derivatives, especially for systems with a larger number of degrees of freedom. Additionally, we have that the time taken to solve the problem is 100 times smaller with analytical derivatives. We also compare the power consumption of the proposed method for different actuation types. The results show that if you can optimize for the stiffness profile, then you have an increment in the energy efficiency. We also experimentally validated the method using robots with different number of active and passive joints, different types of actuation, and different tasks. In all the experiments, we compared the performance of the proposed controller with and without the feedback action. In this case, we notice how feedback improves the overall performance. In the second experiment, we perform a swing-up task with a robot that has the first joint actuated, while the second one is passive. In this case, we notice how feedback improves the stability of the final vertical position. The same task is performed changing the type of actuation. In the previous case, we were considering a constant stiffness, while in this case we execute the task optimizing also for the stiffness profile. This is achieved relying on a variable stiffness actuator for the first join. Finally, we executed experiments with robots with a larger number of degrees of freedom. To summarize, in this work we design an optimal control framework based on DTP for articulated soft robots, which can present both passive and active joints. The method plans the optimal state trajectory, the input, and the stiffness profile. We propose an efficient computation of the forward dynamics and also an analytical derivation of the derivatives. The proposed methods also outputs locally optimal state feedback gains. Finally, we presented the validation of the framework both on simulations and experiments. One of the limitations when controlling soft robots is the use of high gain feedback. For this reason, future work will focus on including limitation on the feedback authority to preserve the natural compliant behavior of the system. Additionally, we will extend this formalism to include environmental contact, and also this formalism will be included into an MPC framework. Thank you for your attention. If you have some questions, feel free to contact.